For today's morning is Rudolf Zeidler from the University of Münster. He's going to talk about distance estimates under lower scalar curvature bounds in the spin setting and beyond. Please.
All right, thank you. Thank you for the introduction, and thanks to the organizers for putting together this nice workshop and for giving me the opportunity to speak here. So let me start out by reminding you of some, classical diameter estimates in classical comparison geometry, just as a warm-up. And here in the beginning, I just want to be clear about the normalization of curvature bounds that I want to use. So I will usually, in the end, talk about scalar curvature bounds, but I will use the normalization in such a way that you would get that kind of bound if you had a lower bound of sectional curvature by 1. That's why always this constant of n times n minus 1 will appear a lot. And we know the classical Bonnet-Myers theorem, which tells us that if we have a lower scalar curvature, lower Ricci curvature bound corresponding to the Ricci curvature of the standard sphere, then the manifold, if it's complete, has to be in diameter bounded by the diameter of the sphere. That's what's written here. And we know a little bit more. In fact, Chang's diameter rigidity theorem tells us that if we realize the diameter bound in this situation, then the manifold must already be isometric to the standard sphere. But my talk will be about scalar curvature. And maybe let's back up a little bit here, because some of you might have not seen these kind of problems before. You might kind of wonder a little bit, can or should we even expect some sort of diameter bounds under lower scalar curvature restrictions? This seems to be a little bit strange because, for instance, if you look at an example like Sn minus 1 times R with the standard product metrics put on there, then of course it's a nice complete manifold. It has a positive lower scalar curvature bound because the scalar curvature on products behaves in such a way that you just get the product of the sum of the two scalar curvatures. So here you get 0, here you get a positive lower bound. So you have clearly a positively scalar curved manifold, which is complete and of course unbounded. Of course, if you want to have something compact of a large diameter, we can replace this by a very large circle, and you also don't get any bound in this case. But turns out maybe we've made our lives a little bit too easy here because we've chosen the sphere. And if we look at examples like that, where we replace the sphere here by something which itself does not support positive scalar curvature, then it turns out something will be possible. And I think this kind of started already in the 80s. Gromov and Lawson proved that if you look at the torus across the real line, then this does not admit complete positive scalar curvature. This nowadays you would maybe prove this using mu bubbles or Callias operators, but this was already known in the 1980s using older techniques. Okay, so this is I guess the first idea, and you can try to make this a little bit more quantitative in the following sense, that maybe you can derive some sort of distance estimate from that. And to kind of see what kind of distance estimate you might get, you can kind of take the opposite point of view and try to find a positive scalar curvature metric on this manifold. I guess we already know that we cannot do it, but let's try it anyway and see what happens or what fails. And the simplest way of maybe constructing some sort of metric here beyond the product metric would be to take a warped product. Okay, then we can let's say, put the standard flat metric on the torus and then put a warped product metric here, where we just use some sort of warping function here on the metric on the torus. And then we can look up the standard curvature formulas and try to compute the scalar curvature of such a warped product. We get that kind of formula. What's important here is that the logarithmic derivative of the warping function appears here, which precisely corresponds to the mean curvature of these totally umbilical slices that you have. And then you can try to set this equal to some positive constant. Let's take our favorite constant, n times n minus 1, and just solve the ODE. Now you can do that, and you get a solution. Looks kind of weird, but you get an explicit solution. So the thing you get, up to, I guess scaling doesn't matter here because you have the logarithmic derivative, but essentially that's the up to some scaling and translations, going to be the unique solutions. Unique solution looks like this. It's some sort of cosine function, but you get this kind of weird root here. Okay. And in the case that n is equal to 2, this gives you the standard Watt product description of the two-sphere. But in higher dimensions, this is something else. So this is not the sphere. Okay, and what you see is that there is some sort of definite time after which this here goes to 0, or like equivalently here, the mean curvature here will blow up at the tips. And no matter what you do, if you do this kind of construction, you will not be able to go any further than an interval of length 2 pi over n. Okay, but that's just, I guess, the most simplest construction you can imagine to do. You could, of course, now ask, can you do some sort of more complicated metric which allows you to maintain a lower scalar curvature bound, but you go beyond this kind of distance of 2 pi over n? And this, I guess, is like one of the motivations of one recent conjecture due to Gromov, which, sure.
So if I took a more, like or if more handles or something, it would be even worse, is that right?
Yeah, I guess the situation would be even worse. But you can sort of always, I guess, approximate the situation by just making this factor very big, and you kind of can sort of get the contribution that you would get from a non-flat part here arbitrarily small. So that's, in a sense, that's the best you can do if it's really flat. But if you had some negative contribution, you could get it arbitrarily small and get approximately this situation as well. Okay, so the conjecture is that now we're looking at some closed manifold, and there are some reasons I'm not going to go into. We want to exclude dimension 4 here, such that it does not admit the metric of positive scalar curvature. And then we look at Riemannian metrics on this cylinder here, so m cross some interval. The length of this interval here does not matter. And we want a scalar curvature lower bound of n times n minus 1. And then the sort of prediction is that the width of the situation, which means the distance between the two boundary components here, must always be bounded above by 2 pi over n, which is precisely the number that we saw in this explicit example that I showed you on the previous slide. Okay, so that's the conjecture, and this, I guess, is part of a bigger program, or like bigger set of questions that Gromov recently proposed, studying some sort of comparison and inequalities for scalar curvature. And I'm today going to focus mostly on this question, but there are sort of others which are in a similar spirit. Just want to mention this at this point. How do you go about proving such things? So first of all, there is this condition here that M does not admit the metric of positive scalar curvature. So you need to have some examples which do not admit metrics of positive scalar curvature. And there we have different techniques to show that we have such examples. And these techniques, then you can try to modify them in a way that you can prove such a result, perhaps. So the sort of standard techniques that we have, sort of one of them are minimal hypersurfaces and mu bubbles, which we've already seen in this conference so far. And especially mu bubbles can be used to prove this conjecture. Initially, Gromov did this for the torus and somewhat related manifolds. And if you go towards mu bubbles, you can actually prove this for all orientable manifolds, at least up to dimension 7. In higher dimensions, you again have the usual GMT regularity issues. We've also seen yesterday in Sven's talk mentioned the space-time harmonic functions. And he also mentioned that there are some applications in Riemannian geometry, and this is one of them. So this is sort of something very recent. It works only in dimension 3. And the sort of third technique that will be sort of the content of my talk, and which has not featured so much so far, are Dirac operators, and then a sort of modification of that, which we usually call Galias operators. What's bad about dimension 5 is that there are sort of special obstruction coming from gauge theory, from Seiberg-Witten invariants in dimension 4, which obstruct positive scalar curvature, but they kind of die if you take a product with the real line or a circle. And they actually give counterexamples to the formulation of this conjecture if you don't exclude that dimension. But the principle kind of still works, and you could give a slightly more refined formulation of this conjecture, which then wouldn't exclude dimension 4, but sort of for simplicity, I wanted to focus on this, but then you have the problem that you have to exclude dimension 4. Okay, but now let me go towards sort of the main content of my talk, the sort of Dirac operator method. So here we start with a spin manifold. I won't tell you the definition, but what's important is that this structure gives us a nice first order partial differential operator, which is elliptic, the spin or Dirac operator. And this Dirac operator, well, it acts on sections of the so-called spinor bundle, and it relates to the scalar curvature via a Bochner type formula, which in this case we usually call the Schrödinger-Lichnerowicz formula. So I guess it was first used in the scalar curvature context by Lichnerowicz, but it was already known in the 1930s by Schrödinger. At least it appeared in a paper of Schrödinger back then. And the idea is that the square of the Dirac, or the Dirac Laplacian, features this scalar curvature term here, and a sort of non-negative operator here, the connection Laplacian. And what this means is that if the scalar curvature term here is positive, then you cannot have any non-trivial elements in the kernel of the operator, because you sort of would get a contradiction from this formula here then. And now if you have some method of always producing sections which lie in the kernel of the Dirac operator on some given manifold independently of the metric, then you can use this formula to exclude the existence of positive scalar curvature metrics. And now you need a method to produce solutions. In the case of closed manifolds, we usually do this using index theory. You can apply the Atiyah-Singer index theorem to compute the index of this operator. And it turns out to be the A hat genus. And this is sort of independent of the metric. Actually, if you just want to know that it's independent of the metric, you don't need the index theorem in full. But you can actually compute it. And you have examples where this is non-vanishing. And if this is non-vanishing, then you can always find a solution in an element in the kernel of the Dirac operator, and thereby exclude the existence of positive scalar curvature metrics. And this, I guess, is sort of the first obstruction result to positive scalar curvature due to Lichnerowicz in the 1960s, stating that a closed spin manifold of non-vanishing A hat genus does not admit positive scalar curvature. Now, there are some sort of variants of this index invariant. Here, this index is just, as usual, an integer. One can now sort of amplify that in a sort of topological way. And one thing is to get a K-theoretic invariant, which lies in the real K-theory of the point. And the nice thing about this is that this is actually a complete obstruction for simply connected manifolds for the existence of positive scalar curvature in dimensions at least 5. And then you can amplify this a little bit further and get a K-theoretic invariant in the K-theory of the group sister algebra of the fundamental group. This is sort of a tangent that I don't want to get into today, but I just want to mention it because these sort of invariants, they are sort of restricted because they only are non-zero in certain parities of dimensions, modulo 8. But this works potentially in all dimensions. In particular, you can deal with the non-existence of positive scalar curvature on the torus with this method in all dimensions. well, it's used in a bunch of ways. Somehow it turns out that the fundamental group is important here, and if there is a complicated fundamental group, then this problem is difficult. But it's in the case that it's simply connected, easier, and that's why sort of you have such a nice result here. Here the story is a little bit more complicated, and I don't want to get into today and go into the more geometric direction. Okay, now this is sort of the basic obstruction theory. Now we need to get to the way of how to prove such a distance estimate. And for this, we have to modify the Dirac operator in some way. And what I'm going to do is, first I'm just going to do some sort of algebraic trick where I double the Dirac operator and add some Pauli matrix here. And then I'm going to choose a function. I call it psi here, but it's going to play the same role as the h in the mu bubbles, or the mu in the mu bubbles, I guess. And what you can do is you just add basically the psi as a potential to your Dirac operator, and then try to get a modified Schrödinger-Lichner-Rovitch formula for this operator. And you can plug this in, you get some formula, and in the end it looks quite nice because it looks, the first part, the same as the original Schrödinger-Lichner-Rovitch formula, but then you get an additional term which involves some differential expression in terms of your potential. And then the way you go about this is you choose your potential in a way that it relates to some sort of distance, and that's in the end how you bring the distance into play into studying this problem of the Dirac operator. So one thing would be to start with some sort of distance function, and then take this potential psi just as a real valued function of this distance function. And here you can take this guy, for instance, this tangent function here, which is sort of related to the mean curvature we saw in this warped product example. And then here, if you compute this out and you know how to derive a tangent, then you get that this is just really minus n times n minus 1 over 4. And this is sort of geared towards, if you now have a lower scalar curvature bound of plus n times n minus 1, or then this sort of expression will precisely cancel out or precisely balance with the lower scalar curvature bound. And then you can play around with this and try to make your operator invertible and get a contradiction to an index and things like that. That's just vaguely how it works. This is the Clifford action, or the, I guess, the principal symbol of the Dirac operator. That appears here. Yeah. Okay, and as was already mentioned before, this can also be interpreted in terms of some sort of space-time situation where you write down a kind of phony initial data set, where as your k you take some function times the metric. And then sort of this lower scalar curvature bound of n times n minus 1 implies the dominant energy condition for this particular initial data set. And then this is sort of related also to witness proof of the space-time PMT. Okay, now the idea is you can sort of use this operator and plug it into the sort of index theory machinery, and then you can prove that Gromov's width conjecture actually holds whenever M is a spin manifold, and this sort of very general Rosenberg index is non-vanishing. This in particular includes all the standard index invariants, and because these, in the simply connected case, this is actually a complete obstruction, you deduce that the conjecture holds for all simply connected manifolds in dimension at least 5. All right, and maybe now let me mention one more result going into that direction, namely a corresponding rigidity result. Here we will study a situation which is a little bit more general, but also a little bit less general. It's more general because we study a general spin manifold with boundary. where we decompose the boundary into two parts. And we know that the A hat genus of one of the boundaries is non-zero, and we impose a lower scalar curvature bound as usual. And in addition, we impose a mean curvature bound. Then we actually get a stronger distance estimate depending on the mean curvature bound here. And moreover, if we actually have equality in the mean curvature bound, then our theorem tells us that the manifold is actually isometric to a product. So there might have been some topology here in the beginning, but in the case that we are in this extremal situation, this cannot happen. And it must actually be a product topologically, and metrically it's a warped product where the warping is given by the function that we've seen in the example in the beginning. And in fact, the manifold must admit a parallel spinor and therefore is actually Ricci flat. And you can deduce from this that, again, that this width must actually be strictly bounded above by 2 pi over n, because this function here goes to minus infinity as L approaches this critical threshold of pi over n. So if you have something, if you have any bound here, you can always undershoot it by just going towards pi over n. All right, now I also mentioned that these kind of results can be applied in the context of the positive mass theorem. So this was, I guess, already mentioned by Dan yesterday. I will sort of give a slightly different formulation or slightly different variation of this, so just for the sake of variety. So if you plug in these ideas in Witten's proof of the Witten's proof of the positive mass theorem, then you can also derive some distance estimate, and you can deal with the positive mass theorem with arbitrary complete ends, as was mentioned yesterday. And here's a variation of this which tries to make this a little bit more quantitative again by considering the following setup. So we kind of want to get a contradiction to the positive mass theorem, I guess. And we start with an asymptotically flat end of negative mass, I guess the kind of thing we don't want. And then the statement is that whenever we want to try to embed this into some n-dimensional Riemannian manifold, then we must somehow violate the assumptions of the positive mass theorem. But the statement is that we already must violate them in a neighborhood of the end where this constant here only depends on the chosen end, or only depends on the end that we started with. So this means that in some a priori bounded neighborhood around the end, either the manifold fails to be complete, either you don't have a lower scalar curvature bound of 0, or because we're using spin, the spin condition fails. Okay, this is of course supposed to be redundant, but since we're using this method, we have this additional assumption. Okay, and maybe finally, let me mention one result which goes into sort of a different direction, because here we're using mu bubbles now. So this goes back to a question due to Gromov, who sort of asked, when does the existence of some hypersurface obstruct the existence of complete PSC on some ambient manifold? Of course, I'm paraphrasing a little bit here. There are some qualifiers to this question. You want to have some non-triviality condition, and now we sort of gave an answer to this question in the following sense, namely, if we have an incompressible hypersurface. Incompressible here is the terminology is borrowed from 3 manifolds, meaning that it's injective on fundamental groups. So the pi1 of m injects into pi1 of x. Then if the hypersurface does not admit a metric of positive scalar curvature, we can actually conclude that the ambient manifold does not admit positive scalar curvature. In fact, we have something stronger in case we have non-negative scalar curvature. We have some splitting result up to a covering. But to prove this, there is an interesting condition which involves spin. So here we have these conditions that either X and M are both almost spin. Almost spin means that the universal coverings are spin. Or X and M are both totally non-spin, which means the opposite of almost spin. And it turns out that these two conditions are necessary. So I'll probably not have time to explain this example here now because I think I'm already over time. But I will just mention this at the end, that here this result we have together with Cecchini and Rede. We now use a geometric measure theory approach using mu bubbles to prove this, but you cannot do this without a spin condition. I think it's often thought that sort of spin conditions are sort of technical in these kind of results, and that's, I guess, in many cases true, like in the positive mass theorem, clearly we don't want a spin condition, but there are also some questions around scalar curvature which, even though you don't use sort of Dirac operator techniques, are intimately related to spin. So you cannot get rid of that completely. And sort of this kind of question where you ask about the hypersurface and positive scalar curvature obstructions is one of them. And I guess let me stop here. Thank you.